Today, armed with what we have learned, we will dive our eyes into the smallest and the largest, the calmest and the most tempestuous of these holes, these black stars, these abysses, these funnels that everyone has heard of, but no one will ever see, at least not directly. Because we will always be reduced to scrutinizing them through the effects that their existence produces on their environment. These bodies of absolute darkness, capable of swallowing and retaining everything, including light, were imagined as early as the 18th century. Then predicted and described in detail by general relativity, before being discovered in large quantities in the universe. In theory, any body, even of ridiculously small mass, can form a black hole. To do this, it is necessary to gather and compact enough matter at a point to exceed a critical density there to curve the space-time continuum, to the point that nothing, not even light, can escape from it. Thus, you could get a black hole by compressing all the matter of our planet into a volume on the order of a small marble, the total mass of the Sun in a sphere about 3 kilometers in radius, or by compressing the entirety of your body into a volume on the order of 1/10 billionth that of a proton. Each time, you'd get a black hole. However, in the current universe, we only know of a single astrophysical phenomenon capable of creating the conditions to spawn these space monsters: the gravitational collapse of giant stars. Stars that, being too massive, once they reach the end of their life, find themselves unable to maintain their balance and come to collapse on themselves under the effect of their own weight, to the point of concentrating and crushing the matter at the center with such force that a point of no return, a critical density is reached. In place of the crushed heart of the star, a residue of superstars is then formed, at the center of which reigns, in absolute darkness, a gravitational singularity, concentrating practically all the mass of the celestial body. Around the limit of the spatial extension of the whole, called the event horizon, it draws the border between the rest of the universe and what, having passed this limit, will remain forever prisoner. These black holes, formed by the collapse of stars, are said to be stellar. Their mass is necessarily greater than 3 times that of our Sun. And they are nothing exceptional, as their number is estimated to be over 100 million in our Milky Way alone. And we have been able to identify about 10 in our vicinity, the closest of them being a few thousand light years away from us, within a triple system. Because black holes are not necessarily alone. They sometimes have a star as a companion, or they orbit around each other. In 2015, the merger of 2 stellar black holes, each weighing about 30 solar masses, shook space by emitting gravitational waves that we were able to detect passing through Earth. We tend to mentally represent these perfectly opaque stars as small holes of compact and cramped dimensions. Except that their size, the limit of absolute and total black, which corresponds to the radius of the event horizon, is proportional to their mass. And since this can be huge, black holes are not necessarily small. The lightest among them, which concentrate the mass of about 3 suns into a sphere nearly 18 kilometers in diameter, are indeed small. But there are so-called intermediate black holes in the cosmos, which, with their mass a few thousand times that of our Sun, have dimensions that are starting to be significant. Thus, a specimen of 2,000 solar masses has an event radius roughly equal to that of our planet. At 24,000 solar masses, its size will be on the order of that of Jupiter. As for those that are still 10 times heavier, they are as voluminous as our star. The precise origin of these monsters of space is still debated. Did they become so massive by swallowing clouds of gas and dust, stars, by merging with other black holes? And this continuously over billions of years? Or did they form from the collapse of hypothetical stars of several thousand solar masses at the very beginning of the history of our universe? The question remains open, just like that of the formation of black holes, called supermassive, which, as their name suggests, possess insane masses, from several million to several billion times that of our Sun. These dark titans have certainly contributed significantly to giving our galaxies their shape, and will be among the last objects to disappear from the cosmos. The most imposing among them can reach truly astronomical dimensions by concentrating the mass of a small galaxy into a volume on the order of that of our solar system. Thus, the black hole Holmberg 15A, whose mass is estimated to be 40 billion times that of our star, measures 118 billion kilometers in radius, which is 20 times the average distance from the Sun to Pluto. These supermassive monsters remind us that, as strange as it may seem, not all black holes are extraordinarily dense. Even the lightest ones we know of, with their few 3 solar masses, have an average density of nearly 2 billion tons per cubic centimeter. A black hole of 130 million solar masses has an average density close to water. As for the heaviest ever observed, with its mass 66 billion times greater than that of our Sun, it has an average density much lower than that of air. Here too, the precise origin of the processes that allowed these supermassive black holes to form remains largely shrouded in mystery. Did they acquire their positively enormous mass by growing excessively over time, cannibalizing everything that could fall into them? Or do they result from the coalition of hypothetical primordial or intermediate black holes? Or perhaps they are the remnants of the gravitational collapse of a giant star? We don't know exactly. Nevertheless, it is believed that the center of each galaxy harbors such a monster at its heart, and the one in our Milky Way is no exception. There we find Sagittarius A, a galactic black hole concentrating nearly 1,000th of the mass of the central bulge. And its presence is revealed to us by the distribution of abnormally fast movements of stars apparently revolving around nothing. Thus, we have been able to observe in our galactic center stars whose revolution revolves around an invisible abyss, a pivot point. Some, by accelerating their course towards the center, can acquire considerable speeds when they pass closest to Sagittarius A, to the point where we have been able to identify, in our galaxy, a star literally leaving it. It is thought that this latter, after passing closest to the supermassive black hole, was seen as if by slingshot effect, confer enough speed to be able to escape the gravitational attraction of the Milky Way to end up, in the long run, wandering alone in space. The tracking and study of this great cosmic sweep of disturbed trajectories. The mass of Sagittarius A has been estimated to some extent, 3 million solar masses, for a radius 17 times greater than that of our Sun. Whether they are supermassive or stellar, black holes can reveal themselves to us through their influence and the gravitational grip they can exert on celestial bodies, sometimes located several light years away. Depending on the varieties of orbital configurations, the most imposing ones can even, when stars approach them, tear off part of their outer envelope, which then leaves, in the wake of the star's movement, immense trails of burning gas. And when some of them venture too close, they can even be torn apart and dislocated by the powerful tidal effects exerted near the orbit, black and bottomless. And then, by draining the matter present in their close vicinity, by ingesting suns or vast clouds of gas and dust. Black holes indirectly reveal themselves to us by starting to shine. Like here, in a tight binary system, in which a black hole and a star orbit each other. We see a part of the outer layers of the star being torn off by the dangerous proximity of its mysterious companion, which has become active, and in a sense visible by matter, which, by diving in its direction, belts an extremely bright disk. This accretion ring, which often forms a thick and opaque twist, is made incandescent by the strong acceleration of the siphoned matter, which comes as if to coil around the hole. In an accelerated spiral movement, the speed of these flows of matter increases, especially since the black holes themselves spin, dragging with them in a dance, which is impossible to refuse anything that gets too close. Because a rotating black hole, the only ones that exist in the universe, does not spin in space like a top would on a table. In the direction of their movement, they distort and drag with them the geometry of space-time, with an intensity that decreases as one moves away from the event horizon. So much so that, in the direction of rotation, the matter that is sucked in and siphoned off is inevitably dragged along, caught up in a swirling movement as if by the force of a current. We have thus been able to identify the presence in the cosmos of black holes, whose surface rotates almost at the speed of light. In these accretion disks, the effects of turbulence produce continuous friction on the gases and particles, transforming them into a plasma soup, heated to hellish temperatures ranging from a few tens of thousands of degrees at the outer limits of the ring to more than 10 million near the center for stellar mass black holes. As for the supermassive disks, their temperature can range from 100 million to several billion degrees at the level of the inner disk, to the point of generating nuclear fusion reactions capable of converting and transforming 10 to 40% of the mass of the siphoned matter into energy emitted in the form of powerful X-ray emissions at the event horizon and gamma radiation bursts in the crown area that forms above the disk. Due to the intensity of these transformations, the total luminosity of the plasma slurry can exceed that of our Sun by several million times. At the same time, the high-speed rotation of the siphoned and ionized matter due to friction can give rise to an intense magnetic field. Its activity can lead to the formation at the poles, along the rotation axis of the black hole, of a bipolar supersonic plasma G made up of radiation and matter flows moving at speeds close to that of light. These supersonic jets are formed when the intensity of the turbulence and the abrupt changes in magnetic field lines come to accelerate the matter inside the disk enough to tear it away from the black hole's sphere of influence and spit it out at the poles. When such phenomena occur on the scale of supermassive black holes, they give rise to what is called a quasar, an extremely active galactic nucleus, the most intensely energetic astrophysical phenomenon in the known universe. Quasars have been identified that are 100 times brighter on their own than all the stars in our galaxy. And if you put the brightest of them 27,000 light-years away from Earth, in the center of our Milky Way, it would shine for us, 10 times more intensely than the full moon. The extreme activity of quasars, just like active stellar black holes, results from the insane friction that the gases and dust of the accretion disk undergo. The difference here is that the scale of distances and the amounts of matter involved can be staggering. To grasp the enormity of the phenomenon, consider that on average, an active supermassive black hole swallows between 10 to 4,000 solar masses of matter each year, to the point where the accretion disks of these can reach several tens or even hundreds of light-years in diameter. Exceptionally, the electronic temperature of Quasar's bipolar jet has been measured at 10 trillion degrees, a temperature 1,000,000 times higher than that at the core of our Sun. On its own, the bipolar plasma showers produced by these extremely agitated black holes can eject the equivalent of several tens of solar masses per day, up to hundreds, even tens of thousands of light-years away. In this image, we can see that the heart of this galaxy, beating to the rhythm of what it ingests, has ended up forming, through the eruptions coming from the accretion disk, an immense gas bubble 65,000 light-years in diameter. One day, the seemingly insatiable appetite of each quasar will come to calm down. The activity in the center will decrease in intensity, because, by constantly drawing from its environment, each supermassive black hole causes matter to dry up and will inevitably become more peaceful. Thus, as each quasar ages after having cleaned its neighborhood, now devoid of matter that could feed the beast, it will come to extinguish. That's why, out of the few 100,000 quasars identified in the observable universe, almost all of these phenomena have been observed in the heart of distant galaxies, located several billion light-years away from us. In other words, we see the intense activity of these quasars as it unfolded several billion years ago. Thus, it is thought that every supermassive black hole, including the one residing at the heart of our galaxy, likely found itself in this state at the beginning of its existence. But let's now leave these turbulent environments to focus on what we would actually see if we could approach a respectable distance from an inactive and calm black hole. Here we are facing a digital simulation made by the researcher and black hole specialist Alain Riazuelo, which puts us in orbit. At 2 million kilometers from a monster of 50,000 solar masses, we can see that the intense space-time curvature, the powerful gravitational effects, distort reality near the hole. As it passes in front of the field of stars, it literally bends the light rays, thus causing gravitational mirages at its periphery. The deflection of light coming from the stars, actually stationary in the background, gives the impression that the stars want to avoid passing behind the event horizon. The circular region in which these seem to rotate is a gravitational lens. An Einstein ring where the image of the sky circulates, located exactly behind the black hole, which deflects the light rays so much that they practically hide nothing. And we almost always manage to see what is located exactly on the other side, distorted. The deflection of light also causes strange effects here. During the transit of stars on the ring, they seem to enlarge and their brightness intensifies until it becomes maximum, when the star is perfectly aligned with the center of the hole. We also witness the birth of duplications, to the appearance of secondary images, always located opposite each primary source of light and slightly less bright. And these duplication effects also concern the entire celestial vault. And here, the entirety of the creamy band of our Milky Way begins to take the shape of a distorted circle surrounding the black silhouette of the opaque star. And it is strange to think that these fascinating stars are also, paradoxically, the simplest in the universe. In reality, nothing in nature is simpler than a black hole, because the behavior of these only depends on three parameters: their mass, their angular momentum, linked to their rotation speed inherited from the matter that gave them birth, and possibly their electric charge. You can look around you for something simpler. You will find nothing. These black stars are characterized by a minimum. And yet, this apparent simplicity envelops them in a thick mystery and challenges the greatest human minds. Because at their center is a region where the distortions of space-time diverge and degenerate to infinity. These gravitational singularities put the current laws of fundamental physics to a severe test. They behave for them as an insurmountable limit, a challenge we struggle with and our knowledge fails to address. It's nothingness, or rather the unknown, of the deep infinities. And as a result, these gaping chasms having seemingly forever carved out space and time. They are also laboratories that galvanize minds and theories. Dark laboratories in which extreme conditions prevail, pushing the study of the laws of nature to their very limits. Here, the dizzying, crumpled and torn curvatures of space and time tear away their meanings. Dimensions lose their continuous character, what studies them, the sense of reality and matter, if they still exist, its properties. And to be able to venture further, we would need a so-called quantum gravity theory, a theory capable of reconciling the study of the infinitely large and the infinitely small, capable of unifying general relativity and quantum physics. However, currently, no physics has managed to fill the void surrounding the question of singularities. Perhaps one day we will find there a key to access other secrets, to open a black box, not Pandora's, but perhaps to the treasure. Consider that in black holes, one of the great unsolved mysteries of modern physics, the information paradox, is nestled. Because each black hole is also a memory hole that keeps no memory of what it has absorbed, given that everything that falls into it is forgotten. For example, it is absolutely impossible to determine, after the fact and with certainty, if this black star was formed from a giant star, or from an innumerable number of compressed old TVs. In other words, nature is the origin of the matter and energy that contributed to its formation. Any information absorbed by a black hole is lost forever. The second law of thermodynamics violated in the process. Going into the details of these notions of order and entropy is to risk leaving a delicious aftertaste in the back of our skulls, of a gaping hole, posing many more questions than it provides answers. But also to open the floodgates. Extraordinary sources of fantasies surround these wells of mysterious, opaque, dense, and dark swords, bending around them the nothingness, space, time, and shadows. To make these extinguished suns that would collapse, creating a passage between a dying world and the other reborn. So, it might not seem like it, but plunging your eyes into the void, it's work. Toss a small coin into the abyss to support our efforts. Subtitling ST501.